All right, what up, my dudes? Okay, let's get into the check your understandings, and I'm going to try to go through this as quick as I can. Okay, so looking at check your understanding number 1. So a beanbag is thrown from a window 10 meters above the ground with initial velocity, horizontal velocity of 3 meters per second. So how long will it take for the beanbag to reach the ground, and then how far will it will travel horizontally? What's its range? Okay, so let's just quick draw a picture, and there is one that's already provided for you. I know it's in the notes. I don't remember if I put it in your or in the note, like the slides. I don't remember if I put it in your notes. But let's quick draw a picture. So it's going to be here's a building, and 10 meters above. So we're going to say this is the window that's going to be 10 meters above. Okay, this is going to be. We're going to say that this is going to be our y displacement. It's going to be from there, so 10 meters. And this guy is being shot out at a rate of 3 meters per second. And it's going to go swoop, bloop, and it's going to hit the ground right here. And we want to know from here to here, what is our range? Okay. So we don't know that. And then also we want to know how long it's going to take. So from the point in which it's tossed out of the window to the point in which it hits the ground, we want to know how long that takes. So let's just start writing down our variables, but specifically writing them down, keeping them separate. So we're going to have our x variables over here. Okay, my x variables are going to include, there's an initial x velocity, which I'll just tell you right now. So here's a cool little trick. So remember, unless it's explicitly told that the x velocities are affected by some sort of acceleration, whether that's slowing it down or speeding it up by some force, if they don't tell us that, it's constant. So this can just be written as just vx. Okay, it's just the x velocity. It doesn't change. And we're going to say the x velocity here is 3 meters per second. We are trying to solve for the range. Don't know that yet. We're trying to solve for time. Okay, because we don't know that yet. And we can say that acceleration for this is 0 meters per second squared. There is no acceleration, so we can remind ourselves that. And yeah, that's pretty much it. That's all we have for the x. Now, what do we have for the y? Well, for the y, we have a couple more things. So we know the vertical distance, and the vertical distance is going to be 10 meters. Okay. We also know gravity. Gravity is going to be, let's say, negative 9.8 meters per second. Okay. What else do we know? Well, we also know, let's see, what else do we also know? Well, we also know that at the point in which this is thrown, we know that it's vertically, its initial velocity is 0, because at the point it's thrown is already its maximum height. Okay, but what we don't know is we don't know the final velocity. We don't know what this guy is. We also do not know the time. Okay. Now, just by looking at the different number of variables that we have available, we could definitely see that our y variable has a lot more to deal with has a lot more to work with than our x. So because of that, we're going to actually solve for time first by using our y-axis material. So now what we should do, we should get out our kinematic equations, and we can just look through our kinematic equations and kind of decide with the variables that we have, what can we use here to solve for time, okay? Because that's really the only thing that we have to solve for over here. Well, I'm trying to place this, we've got displacement, we have acceleration, we have initial velocity, and we're trying to solve for time. Well, to me, that looks like number 2 here is our perfect candidate. It's got displacement, it's got initial velocity, acceleration, and it has time. Okay. And if you think about it, if the initial velocity if we know the height in which this is falling, if we've got initial velocity, 0, we know how long it's going to be falling, and we know the rate in which it's going to fall. I mean, yeah, this is the perfect equation. So we're going to use that guy to solve for time. So let's just quick write it out. So d is equal to vi times t plus 1/2 acceleration times that bad boy. And we got to solve for t. Now I'm just going to do this real quick. So I know that's 0 plus 1/2. And I'm going to be skipping this because we're going to be using this equation quite a bit. Okay, now I'm just going to skip. I'm not going to skip. I'll show you. And then it's going to be 2d is equal to 0 plus 1, or 0 plus acceleration times time squared. And then it's going to be 2 times displacement over acceleration is equal, and I'm just going to get rid of the 0, is equal to time squared. And then time is going to be equal to the square root of 2 times the displacement times acceleration. And if we plug all that in, pop it into the calculator, so that'll be 2 times 10 over, in this case, now, I did put negative. I shouldn't have done that. Let's just keep it a positive. It's going to be a positive 9.8. And the reason why it's positive is that we have vertical motion in one direction, so there's no point in making it negative. If we were to make this negative, we would also just make 10 negative because it's moving to the south, or at least it's moving down, which typically is associated as a negative direction, and it would end up positive anyway. So we're just going to forget about this. But this will come in handy when we get into actual projectile motion, like at an angle with angular motion. Okay, so the time that this thing was fallen outside of the window, it's going to be the square root 2 times 10 all over 9.8. It looks like what we should get is that we should get 1.4 seconds for our answer. So this bad boy is going to fall out of that window for 1.4 seconds. Okay, so now we've got to ask how far, so how does this work? So how does this work horizontally? Well, just remember, the point in which it hits the ground is going to be the same, it's going to be the same horizontally or vertically, right? Because it's the culmination of the two, it's the addition of these two vectors, of the horizontal and the vertical vector. Okay, so the time is constant, or at least in this case is the same for both the time it takes to go from here, or from here to here, as it is to go from here to here. Okay. It just so happens that when you put them together, it's going to be out here. So that's why we use y, and that's, for the most part, generally speaking, why this is the answer for both the x-axis and the y-axis. So 1.4 seconds, 1.4 seconds, which is awesome. So now we've got something to work with over here. Okay, so let's work with it. So, okay. So now all we got to look at, and this is why I want to show you that this is just Vx. The reason why I want to show you that was for this reason, is that this is the final and the initial. There's no change. So it's just 3. So if you have you've got your velocity, you've got time, and you're trying to find displacement, well, I mean, come on. It's just going to be good old classic. Velocity is equal to displacement over time. Okay, and then we're solving for displacement. So then that's going to be displacement is equal to our velocity, our horizontal velocity times our time, since we now found that. And we'll find out here it's going to be 3 times 1.4. And our displacement is going to be 4.2 meters. And we could say, horizontal. Boom. And we have our answer. So, again, answer for time for A. So this is our answer for A here. This is our answer for B. This whole thing took 1.4 seconds. So one Mississippi, 2, and then pretty much that's it. Or 2 Miss, whatever. And then it traveled 4.2 meters horizontally. So this right here in our picture, to kind of associate with our picture, means it went 4.2 meters this way. and the time it took altogether was 1.4 seconds, which again is really nothing at all. Okay, so this was check your understanding number 1. So let's now take a look at check your understanding number 2. Okay, so check your understanding number 2. A hockey puck is launched horizontally from the roof of a 32-meter tall building at a velocity of 8.6 meters per second. What is the hockey puck's time of flight? What is the hockey puck's range? So this is literally the same exact problem with really nothing different at all. So again, let's draw a picture. So here's our picture. Here is our poorly misshapen hockey puck. And a poorly misshapen loaf of hockey puck is going to be shot out this way, and he's going to be shot out 8.6 meters per second horizontally. And he's going to go all the way down here to the ground. And the height of this is going to be 32 meters. Okay, so this is going to be our dy. Okay, we got that. That's what we're given. So now we've got to solve for everything else. So let's just do what we did again. We're going to separate between x and y components. So over here for x, we have our horizontal velocity, which is going to be 8.6 meters per second. We're trying to solve this. We're trying to solve from this point to this point. Okay, that's going to be our x, our horizontal displacement. We're going to solve for that, so we don't know what that is. Okay, we need time. We don't know what time is. We know that horizontal acceleration is 0, and that's pretty much it. That's all we know. So again, as we can see, we don't have a lot of work with over here. We've got to be working with this over here. And we should know that before we even fill this in by now. After doing the last problem, you know, this is pretty much the same thing. So what do we have? Well, we know that because this is the max height, we know that the initial velocity is going to be 0 meters per second. We don't know the final velocity. We don't have to solve for this one on this problem, but we don't know this one. We do know gravity. Gravity is 9.8 meters per second squared. And we don't know time, but we do also have our y displacement, and our y displacement is going to be 32 meters. Okay, so this is what we have to work with. So just like the other side where you got to solve for time, and to solve for time, I'll just write it this time, solve for time. We're going to be using this guy. Now, since I already walked through on how to solve for this, I'm just going to show it, and then I'm going to jump forward to the last, like when it's actually solving for time. So that's the equation we're using. I think that's number 2. Yeah, this is kinematic equation number 2. Okay, and then to solve for time, it's going to be the square root of 2 times d over acceleration, 2 times 32, all over 9.8. And that's going to give us, and what that should give us is 2.6 seconds. Okay? So from the moment it leaves the top of the building here until the moment that it hits the ground, 2.6 seconds. Okay? So there's the time of its flight. Okay, so now, and that's for A, now we need to solve for B. So what's the hockey puck's range? So at the moment it leaves the edge of the building to the moment it hits the ground, what horizontally, how far did it go? This is going to be the same exact thing as last time. This is going to be your Vx is equal to delta D times T. So we're going to solve for D here. And we're going to see that we get 8.6 times our time, which is now 2.6, which I realize I didn't write up here. 6 seconds. And what we should get here is we should get 2.2, we should get 22. We should get 22 meters. And again, we can say 22 meters forward. If you've got a picture like I do, you can have 22 meters with an arrow, whatever works. Okay. So that is check your understanding number 2. Now, this was projectile motion as far as leaving a building. Okay, this is as far as, no angular motion. So let's start looking at angular motion. Okay. So angular motion here. Let's take just a quick peek. So for that's going to be number 3. Check your understanding number 3. A soccer player running on a level playing field kicks a soccer ball with a velocity of 9.4 meters per second forward at an angle of 40 degrees above the horizontal or the horizon. Determine the soccer ball's time of flight, the range, and the max height. Okay, so let's take a look here and draw a picture what's happening. So here's our level field. Here's our soccer ball. And our guy's going to be kicking this guy 40 degrees above the horizon. And not only is he kicking it 40 degrees above the horizon, he's kicking it with an initial angular velocity of 9.4 meters per second. Okay? And that ball is going to go, bap. So what we have to do is we have to find the time it took to do this. We have to find the range, which is going to be the displacement on the x-axis. So from here to here, what is this distance? And then we're also going to find the maximum height. So that's going to be from here to the ground. Okay. So this is just to associate. And no, this is tiny, but here's this. Here's this. Okay. That's what we're looking for. And then also the time. So we're going to split these up into x components and into y components. Okay. And then actually we can also, and we can just write this because it's the same for both sides. Our initial angular velocity is 9.4 meters per second. What we don't know yet is we don't know our initial y velocity. We don't know our initial x velocity. We do have theta. Theta is 40 degrees. What else do we have? Well, we also do have gravity. Gravity is 9.8 meters per second. What else do we have? Well, we know that the acceleration over here for x, that's going to be 0 meters per second because, again, there's no extra force being applied. Okay. We don't know this guy yet. We also should know that this up here, it's the same thing. So because we're not told that there's a force applying in the x direction, we should know that our initial velocity of the x axis is going to be the same as the final velocity in the x-axis. Okay. So we should know that. We're trying to solve for displacement. We're trying to solve for time. What's our max height? And then what's our time? Now, same thing. We should notice we have way more information, even before we solve for these right now. We have way more information over here than we do over here, or at least usable information. Oh, and I forgot. We also don't know the final velocity in the y either. Okay, we just don't know what's going on, or we don't know enough over here to know, for instance, to solve for time. So let's now solve for these guys. So that was that equation that was part of the notes. It's going to be the Vix, the initial x velocity is going to be the cosine of theta times, that's going to be the cosine of theta times the initial velocity, angular velocity. Whereas the initial y velocity is going to be the sine of theta times our initial velocity. So real quick, if you're wondering why this is cosine, well, think of it in this way. When that soccer ball is kicked, if you notice, there's a triangle here. Okay, this right here is a triangle. So if your x is here, your y is here, and this is your angle, opposite over hypotenuse, adjacent over hypotenuse. Hopefully you got that. So, okay. So now we just got to solve for this. So just plug them in. Let's just plug these in. So this is going to be the cosine of 40 times our initial, which is going to be 9.4. So our initial x velocity in this case is going to be 7.2 meters per second in this direction, just because that fits with our picture. And we can write it up here, 7.2 meters per second. And then our initial y velocity is going to be sine of 40 times 9.4. And what we should get is we should get 6 meters per second. And in this case, it's going to be in the upwards direction, okay? And then we'll write that over here. We've got 6.0 meters per second, okay? Okay, so now we've got some to work with now. Okay, so the first question is going to be about time of flight. So in order to find time of flight, what we need to do, and again, because we have more information over here than we do here, we've got to focus in on our y. And the time it takes to go from you know, or the time it takes, and this is where it gets tricky, because this is what we have to break down, we have to think of. With the available materials, the variables we have to think critically about how it's going to work in our picture. So this is what I mean. So in order to find the total time here, what we have to do is we have to first find the time it takes to reach the maximum height. We can't just find the total time it took to go from here to here, because we don't have enough information on the horizontal. What we have to do is we have to break down the vertical into two. So first we have to find the time it takes to get the maximum height, and then we have to find the time it takes to go from the maximum height to reach the ground. So we have to find two time intervals. Okay, and it's mentioned in the notes. So let's solve for the first time interval. We're going to solve from the time it's kicked to the time that it reaches its maximum height. So let's do that. So the time it takes to reach its maximum height, using our variables up here, okay, and looking at our variables, we can figure out, you know, maybe which one would be best to use. Okay, so we've got initial angular velocity. We've already used that, but we've got initial y velocity. We have 40 degrees. We've got 9.8 meters per second. We have final velocity in the y direction. Okay, we actually do have this. I accidentally put that. I was thinking the wrong final velocity. We actually have this. It's 0. Okay, at least to the point in which we're going to the maximum height. So, and this is where you got to really keep things straight in your head, okay? Because this is where it gets tricky. So again, our initial velocity is going to be 6 meters per second at the time it's kicked. It's going to be 0 meters per second at the time at which it reaches its maximum height. Okay, so we're going to use those guys. So finding max height is what I'm going to, or finding in this case, finding time to max height. We know that our final is going to be 0. Our initial is going to be 6. We also know gravity. And this is where I mentioned about gravity being negative or positive depending upon your direction. So because it's moving upwards, we're going to associate upwards direction being positive. So gravity is going to be negative. Okay. What else do we have? We're solving for time. Now this is what's so great. What's so great is that we can tackle this in multiple ways. So we could just find the time. We can find the time to the maximum height here, or we could find the maximum height with the given information. It really depends upon what you want to do, because you could use a different number of equations to find both of them, you know, relative at whatever pace. But right now we're just going to find the time to the max height because that's what it's asking for. or at least the total time. So we're just going to use this. I know that I've got acceleration. I know that I have final velocity. I know that I have initial velocity. I'm trying to find time, at least until I reach my maximum height. So I'm going to solve for time here, and what I should get is I should get 0.61 seconds. Okay, that's what I should get. So the time it takes to be kicked to reach its maximum height, it's going to take 0.61 seconds. Okay. Now, you have to ask yourself, or at least you're probably asking Mr. Sheeline, okay, what about the other half? I'm glad you asked. So remember, this isn't, because we're kicking this on a level playing field and there's no air resistance, the velocity and force that we kick it at from in the place it rests here at this angle, the time it takes to reach its maximum height will be exactly the same time it takes to hit the ground. So why? Well, because as soon as it leaves your foot and leaves the ground, gravity is affecting it exactly the same way from the moment you begin to the moment it ends. Okay? So meaning, that's your time. This is, again, time from kick to max height. And because this is on a level playing field, that meaning it's going to land on the same plane horizontally as it began, all we got to do is multiply this guy by 2. And so our total time here is going to not be 0.61, it's going to be 1.2 seconds. So this is our total time of flight. Okay. So if you still have troubles understanding this, you can ask me in class, but pretty much it's because of the fact that of what I explained. We're kicking it here, it's on a level playing field, and the time it takes to reach the maximum height will be, in this case, exactly the same time it takes to reach the bottom of the earth back to the ground, because gravity is affecting it the exact same way the entire time. Okay? Okay, so we found that, so that's A. And I'll show you a quick little thing just to double check if you don't believe me after this. Okay, so now let's try to solve for B. So let's try to find max height. So we've got time now. So time is 1.2, not 1.2. In this case, for finding max height, it's going to be 0.61 seconds. And again, we have a different number of equations that we could use in order to find this, but just because, we should probably use this one over the other, we're going to use, actually I'm going to put it over here, we're going to use this equation. The displacement is equal to initial times time plus 1/2. And what you should get when you plug all that in, because it can stay just like that, once you plug all that in, what you should solve for then is that you should solve for, what you should get is 1.8 meters in the upwards direction. Okay? Now, let's say that you don't trust that. What's another way you could solve for this? Another way you could solve for this, or even let's say if you wanted to start a little earlier, let's say before you solve for this guy over here, there is also this equation that will work just fine as well. Okay? This one will work just as well. The only thing you got to remember, though, is that when for both of these, it's a negative. It's negative 9.8 meters per second squared, because we're just going to max height. Okay, so that means that gravity is working against our velocity. And what you should get here is you should get the same thing. You should get your y displacement being 1.8 meters in the upwards direction. Okay, so that's B. And then C, the max height, or we got C. Oops, I got these, or I just solved for C. Sorry, this is C. Now we got to solve for B. I'm sorry. And let's go back up here to solve for B. And then to solve for B, well, we found time, and time is 1.2 seconds. Okay. We found in this case, we found our max height, and it's 1.8 meters. Okay. Now we just got to find our x displacement. Same thing as last time. This is going to be our x velocity equaling to displacement over t. we're going to solve for d. So d is going to be equal to Vx times time. And what we should find is that our horizontal displacement, our range, is going to be 8.6 meters. 8.6 meters, and it'll be 8.6 meters. And in this case, like in that direction, according to our picture. That's not 18, that's 8. 8.6 meters. Okay, I accidentally started boxing that in early. 8.6 meters. Okay. So, and this is just one problem. So I understand, like it's not terribly complicated, it's just busy. That's the best way I can describe it. It's not complicated, it's busy. Okay, so that's how we solve for this. Real quick, instead of walking you, now that you've seen this, I'm going to walk you through the next one because it is a little bit more complicated. I'm going to walk you through the next one, but then the final one, the medieval one, what I'm going to do for that guy is more or less just show you the, I'll walk through the setup, but then you've got to solve it for yourself. Find the answer for yourself, because it's going to be just like check your understanding number 4. Because I know this video is getting pretty long already. So okay. Let's take a look at this. So a golfer is trying to improve the range of her shot. To do so, she drives a golf ball from the top of a steep cliff 30 meters above the ground where the ball will land. If the ball has an initial velocity, angular velocity of 25 meters per second and is launched at an angle of 50 degrees above the horizontal or the horizon, determine the ball's time of flight, its range, its final velocity just before it hits the ground. So this is that problem where I told you about, yeah, we've got a golf ball here. It's going to be launched, and it's going to go woo. And we've got a number of different things being applied here. We've got a cliff, and the cliff, we're going to say the D of C, the cliff, is 30 meters. We've got an angle here. We have an angle here of 50 degrees. And we also have an initial angular velocity of 25 meters per second. And what we've got to find out, we got to find out this guy right here. And we also have to find out this guy right here. And we have to figure out this guy right here. What's our time? What's our vertical displacement, or sorry, horizontal displacement? What's our vertical displacement? Okay. Now I've already started to draw it, so this is what we should think of. So when we look at these cliff type problems, top of building type problems with angular velocity, we should immediately do this. We should associate and draw dotted lines for our planes. So what I did here is I made a dotted line for my horizontal plane. And that's going to be important because with the information I have, I've got to find define the maximum height this thing travels, which I guess I don't need to find. I don't actually need to find this entirely. It's going to be part of the calculations, don't get me wrong, but it's not what it's asking for. It's going to ask for the final velocity before it hits the ground. And so I'll get to what that is at the end there. So sorry, I interrupted myself, but you want to draw this horizontal line here as if it's a level playing field from the point at which it's being, projected. Because we got to break down the time interval between here to here, and then we can break down the time, and then we can do another time interval from here all the way down to here. Okay, so we have our total time. So let's break this up into x and y components. So on the x axis, we've got, and I'm not going to put the initial angular velocity. I'm just going to quick put down, just because we know how to do that now. I'm going to quick put down the x initial x velocity, which is going to be 16 meters per second. For our y, and that is our initial. Our initial is going to be 19 meters per second. Okay, what else do we have? Well, we know that acceleration in the x on the x-axis is 0. Well, what else do we know? Well, we're trying to solve for time, and we're trying to solve for displacement. Don't know those guys yet. That's pretty much all we can look for in the x-axis. What about the y-axis, other than what we just put in? Well, we've got that. Well, we kind of know part of, we've got the cliff. I'll put the cliff over here as part of the y-axis. We don't know the total height yet. I'm going to say that this is how I'm denoting the total height, is delta dy. We don't know that yet, but we know it's going to be plus, yeah, I'll draw it like this. It'll be the displacement, the d of y is going to be whatever we're solving for, but plus the delta dc. Because what we're going to solve for is this distance to this distance, right? From here to here. So, that's how I'll write it. I don't normally write it like that, but I'll write it for this video. We also know gravity. Gravity is negative 9.8 meters per second. Now, negative, I'm just going to do this, just a downward arrow. Okay, so it'll be implied that when we're focusing on our max height, it'll be negative, but then once we're focusing on from here to here, it'll be positive. Okay. We are also, what else do we don't know, or we do know at least the final y velocity for max height. We know to find max height is going to be 0 meters per second. And I'm going to say in the upwards direction. I know that seems kind of weird, but it's in the upwards direction, and this is also in the upwards direction. And then we're still trying to find time. Okay, so for the most part, this is pretty much the same. Same thing as the other side. So I'm going to kind of fast forward through this just to find, and I'm going to actually break this up. So from here, from our golf ball to max height, this is going to be T1. And then T2 is going to be from here all the way down to here. So to solve for T1, it's going to be exactly the same thing as the other side. And I'm going to put over here T1 plus T2, just to keep things so we understand. So to find T1, so that is going to be the time it takes to go from the top of the cliff to max height. It's going to be exactly what I did on the other side. And what you should get for T1, here, I got to sift through my notes here. So what you should get, and you can use this, you can use like this formula here, because we know all of these variables. What you should get is you should get T1 equaling 1.9 seconds. Okay. So from here to max height is going to take 1.9 seconds. Okay. And then from there, now that you have that, you can solve for displacement in any way you like. Again, if you found your max height before you found this, you can use you can use this equation. So you can use the VF squared equaling VI squared plus 2AD. And what you would find is that with this equation, displacement is going to equal 18 meters. That's going to be the y. Okay, that is 18 meters. What am I thinking? Sorry. You could use another one. You could use, now that you have time, you could, if you wanted to, you could use the average velocity equation if you wanted to. It doesn't really matter. But anyway, what the answer is, though, is to your max height at this, from this horizontal plane that we drew from, an extension of the cliff, from there to there is 18 meters. But overall, because we don't want just the 18 meters, the 18 meters are great, but what we want is the overall height. So from the max height to the bottom of the, I guess in this case the canyon, since we're on a cliff, and that's going to be that 18 meters plus the 30. So overall, we are going to have a total vertical height of 48 meters. Okay. So So again, from here to here is going to be 48. Now, why is that important? Well, the reason why that's important is we need to know, okay, we've reached max height. We're no longer moving upwards. Our initial velocity is now 0. We've got to figure out, okay, let's have gravity do the work. You know, how long is it, how long is it going to take to hit the ground? How long will it take for gravity to affect this golf ball to hit the ground? Wow, that sounded weird. How long will it take to hit the ground is what I'm trying to say. So now let's define T2. Now to find T2 though, this one we have just way more information, you know, available. So here we could use this guy. Again, you've got a number of ways that you can solve for this, but so now to find T2, I'm going to actually write down the variables we have to work that we have available to work with. So we know now that the initial y velocity is actually going to be 0 meters per second. We don't know the final velocity in the y direction. We know that acceleration due to gravity is going to be a positive 9.8 meters per second. Now we know that our total height, I guess you would call it, is 48 meters. And we're trying to find T2. So T2, looking at this, again, there's a number of things we can use, but probably the best one is going to be this. D is equal to VI times T, and I told you we're going to be using this guy a lot. Even in practice, we're going to be using this guy a lot, outside of notes. Now, we've already done this one again, so I'm going to just solve for T2, and what you should get for T2 is 3.1 seconds. Okay, so recap. What is this 1.9? 1.9 is from here to here. What is this 3.1? That is from here to here. So we have our total time now. And our total time, oops, I'm actually going to, just because I'm running out of space here, total time, we'll say, yeah, up here. So total time is going to be 3.1 plus 1.9, which is going to give us a 5.0 seconds. So 5.0 seconds. So the time it took to hit the ball and for it to land at the bottom of the canyon or the dell, whatever is down there, is going to take 5 seconds, roughly speaking. Okay, so that was A. It's a lot of work just for A, I know. Okay, no B plus, I'll just write this down here. 1.9, 5.0 seconds. Total time. Okay, so there's A. So now B, the range. So from here to here, what is our range? Well, this one again, actually I'm going to use this space in here to find the range. So this will be B. Same thing, we have our x velocity, 16 meters per second. We have now the time. Total time is going to be 5. Now we just got to find D, and the x, because we don't know what that is. We've done this before, so that's going to be displacement times our velocity times time. And what we should find is that D is now equal to 80 meters. And we'll say in this direction. There's B. I'll write B again there, so you just know. So there's B, 80 meters, because that'll just be 16 times 5. Okay. Okay. Finally, C, it's final velocity. So what is the final velocity? Why does it only say final velocity? So when we ask for final velocity, notice that it's the same language as in the question right here where it says if the ball has an initial velocity of 25 meters per second at this angle, blah, 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 we should notice that the language is the same. There is no explicit indication if it's on the x-axis or the y-axis. So because of that, the final velocity is not the y-axis velocity that we're solving for. This is the hypotenuse. Gasp. Mr. Sheeline, well, what do you mean? This is what I mean. So real quick, just to draw a bigger picture of what happened here. So golf ball went kablooey. And it's going to go, woo, about. And I know that's not the best drawing for this, but. So, What that means is that because this is we found this is 48, we know this is 50, we know this is 25 meters per second, okay? What that means is that what we're doing is we're going to combine our vectors here. We're going to combine this vector and we're going to combine this vector. And specifically how we're going to combine them is going to be like this. Horizontally, we went 16 meters per second. But then finally, after it has reached its max height, it goes from here down. Okay. Now because this doesn't change, we can just say that this is what that is. We don't know what this is yet. But this is still not what we're looking for. This is what we're looking for. This is what we're looking for. Okay, that's what we're looking for. The only way it would be asking for this is if it explicitly said, determine the ball's final vertical velocity before it hits the ground. But because it doesn't say the final vertical velocity, we are looking for this. Okay. So, and I know, thank you for being patient. We're almost there. And I know this is a lot. It's just, again, it's busy, not complicated. So we've got this already, because remember, this doesn't change. Its initial is going to be its final. This guy does change. So how do we know? Well, we know that its initial y velocity, again, from here to here, is going to be 0. We are solving for the final. Okay, solving for the final. We know, and this is why it's important that we broke these into 2 time intervals. We've got the time interval for this, and this is going to be t2. And t2 was 3.1 seconds. We also know acceleration due to gravity, which is 9.8 meters per second, okay, squared. And that's really all we need. Well, sorry, no, we need a little bit more. We should need a little bit more. We really don't, but it helps. But we also have displacement. Displacement's going to be 48 meters in the y direction, okay. So now we're bringing everything together. Everything we've solved for, we're putting it all together. So now to solve for this, again, there's a number of ways that we could solve for this. Arguably the easiest one here, because we're trying to find the final velocity, we can just use acceleration equation. Okay, just solve for VF. And I've done this one before, so we should know how to solve for VF. But what we should get VF is equal to acceleration times time plus initial velocity, which is going to then equal to our final y velocity here, equaling to 30 meters per second. So this is how quickly it was moving in the vertical plane right before it hits the ground. Okay. But again, we're not done yet. That's not what it's asking for. Okay. It's not what it's asking for. It's asking for this. So in order to find this, we need to find 2 things. We need to first find this guy, and then we need to find this guy. Or we can find both at the same time. It doesn't matter. So in order, we can find theta. And theta, you can use, tangent. Or you can use SOHCAHTOA. You can use SOHCAHTOA for all of this. But to find this guy, if you want to find that first, then it's going to be the tangent of theta equaling opposite over adjacent. And what you'll find is that using that, you're going to find that it's 62 degrees. Okay. And then you can just use Pythagorean's theorem to find this guy. And using Pythagorean's theorem, which is going to be 16 squared plus 30 squared, found the square root of that's going to give us VF. VF is going to then give us 34 meters per second. And then to tie it all together, to label it, it's going to be 34 meters per second, 62 degrees below the horizon. So how do I know it's below the horizon? Well, if I just look here at my triangle, this right here is going to be this horizon. really just this as well. It's moving downwards, okay? Because again, our general motion of this whole ordeal is in this direction, okay? Or at least, sorry, from here to here, it's in this direction. It's in this direction, so it's below the horizon. And this is our final answer for C. 34 meters per second, 62 degrees below the horizon. Okay. Oh. So that is number 4. That is number, check your understanding, number 4. And like I said, I'm only going to help you set up, check your understanding, number 5. Just going to help you set it up. I'm only going to walk you through, splitting up the X and Y components and also drawing the picture. And then the rest will be up to you, because I just walked you through how to do it. And this one is asking the same exact questions. So a medieval prince trapped in a castle wraps a message around a rock and throws it from the top of the castle wall with an initial velocity of 12 meters per second at 42 degrees above the horizon. The rock lands just on the far side of the castle's moat at a level 9.5 meters below the initial level. Determine the rock's time of flight, the width of the moat, velocity on impact. So let's draw this, and there's already a picture that's provided in my notes. I don't remember if I put in your notes. But we got a dude. And that dude, oh, and this is water because it's a moat. I'm going to make the waves the same height. Just so it's nice and even. Same height as my land here. And this dude is going to toss this message, this poor prince is going to toss this at this plane right here, at this angle, which is 42 degrees, at a rate of 12 meters per second. And it's going to go woo, boop, and it's going to hit, we're going to say it's going to hit right at like it says there actually, it says, just on the far side of the castle's moat. So more or less it's landing right, we'll say right smack dab at the edge of the moat. It's going to land right here. Okay. So we've got to determine the time that it takes to go from here to here. We then also have to determine the width of the moat, so from here to here. And then we have to measure the velocity of the impact. So meaning after we have found the max height from here to here, and then add it to this height from here to here, which is going to be, 9.5. Okay, so again from here to here is 9.5. We're going to then use from this distance, this vertical distance, to find the vertical final velocity, and then we're going to use that vertical final velocity to find then the overall final velocity, like we did in the last problem. Or I should say that you will find like you did in the last problem. Okay, so let's just break this down into X and Y components, and this is just going to be the beginning X and Y components, just to reinforce, what we're looking at here. So on the X-axis, we're going to have X velocity, and the X velocity after doing your calculation, your initial X velocity here, and your final, realistically speaking. Let's see, where is it in my notes? Why don't I see it in my notes? Skibbity wop bop a doo. It's 8.9 meters per second. Okay. What else do we have? Well, we've got theta, which we can, I guess if you want to write theta, you got theta. I guess if you want to write down initial angular velocity, we've got that of 12 meters per second. Okay. What else do we have? Well, not much. Trying to solve for this. You know that acceleration is 0 in the horizontal axis. I'm trying to solve for time. Okay, so what do we have for the y? We have our initial y velocity up to the point in which it reaches its maximum height, which is going to be, let's see here, Where is it at? It's going to be 8 meters per second. Okay. This is in the upward direction. This is in this direction. What else do we have? Well, we know that up to the point at which it reaches its maximum height, it's going to be 0 meters per second for the final y velocity. We've got gravity. Gravity is going to be 9.8 meters per second squared in the downward direction. We know that the initial after it has reached the point of its maximum height is going to be 0 meters per second in the downward direction. We know that the final, or we don't know what the final y velocity is yet, but that's also going to be in the downwards direction. We are trying to define time, and we're trying to find, we're going to say that this is max height, which is going to be equal to, I'm going to put a y up here just so it makes sense to you. It's going to be equal to y plus 9.5. And those are all of, and I guess I'll write over here just so, because theta and also the initial angular velocity, just so I don't confuse you. Like, they should be in their own little column, but I'm just not making it. But those are all your variables to use throughout the entire problem. I'll just give you the answers. Yeah, I'll write down the answers real quick for you. But this is what you should solve for. So you should solve for your total time. So total time of flight should be 2.4 seconds. And that one is for A. B. Let's see B. Where is it? It's width of the moat. Width of the moat should be 21 meters. And then your final velocity should be 18 meters per second, 63 degrees below horizon. And those are the answers you should get. So solve this on your own. Hopefully you should come up with those answers. If they're a little off, you know, if you get like 2.5 or you get 2.2, that's fine, close enough, you know, relatively speaking. Because these answers, if I've just been doing these answers, and again, I don't have you guys keep sig figs, but I've been doing, you know, keeping sig figs just so it's easier for me in the future to understand why I get the certain answers that I do. But because I keep sig figs, you may get some a little different. So, okay, my goodness, this is going to be a huge file of a video. So if you guys still have any questions over how to solve for this, please ask me in class as soon as possible. Send me a remind text, send me an email, whatever it is, and I'll try to get back to you. But that is walking through those check your understanding. So I will see you in the next video, guys. Thank you.